In this video, we're going to just take a look at the introduction to the mole concept in chemistry. This might be the first time you've seen it, or it might be a review. So the mole is one of the most important concepts in chemistry because it's the fundamental unit by which we measure amount of things. Having said that, its definition is rather obscure, kind of confusing. This is the definition that's based very closely on that of UPAC. Take a look and see if this makes sense. It's the amount of substance that contains the same number of entities equal to the number of atoms in exactly 12 grams of pure carbon-12. Now let's break that down. Suppose that you had a sample of pure carbon, so maybe a diamond, maybe a piece of pencil lead, and that carbon sample was unusual because where most carbon samples are a mixture of isotopes, this carbon sample is pure carbon-12, so it's this one isotope of carbon. And its mass is exactly, not a little bit more, not a little bit less, it's exactly 12 grams. Well, then the number of atoms of carbon in that sample would be a mole of carbon. Now, if you had some other substance with an equal number of entities, and we'll talk about why that word is used in a moment, then you'd have a mole of that substance as well. All right? Now, how many atoms are there in exactly 12 grams of pure carbon-12? In other words, how many atoms are in a mole? How many things are in a mole? The number that's in one mole is called Avogadro's number, named after an Italian chemist, Amedeo Avogadro. And it's one of the best measured quantities in science. The symbol for Avogadro's number is a capital N number, and then a subscript capital A for Avogadro. Be sure you don't use a little a there, or it'll look like the symbol for sodium. In this representation, look at all these significant digits. 6.022141799 times 10 to the power of 23. All right? Now that top definition we had there is really so irritating to lots of chemists and physicists that they have petitioned UPAC to redefine the mole. There's people that want to redefine it and say that a mole is simply the number equal to this many things, right, or something like that. They want to phrase it as 1 mole is 6.0221499 times 10 to the 23 particles or entities. By using that definition, there will be no mention of mass, 12 grams, or an isotope like carbon-12. At this point, UPAC has not adopted that new definition, but they seem to be moving that way. Now, why did this say at the top there, this weird phrase, entities? Well, take a look at these 3 examples underneath Avogadro's number. If you have 1.000, so pretty much exactly 1 mole of aluminum metal, you would have 6.022 times 10 to the 23 atoms of aluminum, and notice the word atoms there. Also notice that we don't ever really use all those significant digits in Avogadro's number. For us, we'll usually just say 6.022 times 10 to the 23. So why did we use the word atoms here? Well, the word atoms is used because we were talking about aluminum metal. Aluminum, if you were to magnify it down to the particle level, is made of simply atoms of aluminum. So in this case, you have Avogadro's number of atoms in 1 mole. On the other hand, if you were talking about water is not an element, it's a compound, and more specifically, it's a covalent or molecular compound. Then if you had 1 mole of water, you'd have Avogadro's number of water molecules. So notice now we're talking about molecules because water is a compound and a molecular compound. Ionic compounds are a little bit more problematic because in an ionic compound there are no molecules. If you magnified sodium chloride down to the particle level, you'd see that every sodium ion is surrounded by 6 chloride ions, 4 around it like this, and 1 behind and 1 in front. So every sodium has 6 bonds to chloride, and every chloride ion is surrounded by 6 sodiums as well. So every chloride is bonded to 6 other sodiums. There's no identifiable molecule within sodium chloride. Instead, we see a ratio of 1 sodium for every 1 chloride, and therefore we write NaCl as the chemical formula. However, we want a phrase, we want a term that we could use like molecule, so we use the term formula units to refer to 1 sodium and 1 chloride. That pair is a formula unit. So for ionic compounds, we don't talk about atoms of the compound because it's a compound. We don't talk about molecules because there are no molecules. Instead, we use the phrase formula units. So because there's different terms, atoms, molecules, formula units, the definition of mole at the top talked about the number of entities equal to the number of atoms in 12 grams of carbon-12. So that's why that word entities was used. The mole is so important in chemistry. Here's a chemical reaction that's balanced. This is the decomposition of hydrogen peroxide. And if we were to read this at the beginning of the unit, we probably would have read it as 2 molecules of hydrogen peroxide decomposing to make 2 molecules of water and 1 molecule of oxygen. But from here on in, we're going to stop looking at that as made of molecules and atoms, and instead we're going to be looking at it as moles, the mole concept. In the same way when you go to talk about eggs, buying eggs at the department store, at the grocery store, you don't talk about buying individual eggs, you talk about buying dozens of eggs, things like that. So we're not going to talk about individual molecules in a reaction, we're going to talk about moles of the substance. So we're going to read this now as 2 moles of hydrogen peroxide decomposing to make 2 moles of water and 1 mole of oxygen. The mole is the SI unit, the International System unit, for amount in chemistry. It's hugely important. Related to the mole, and very, very important as well, is the idea of a molar mass. And just like that name sounds, it's the mass of 1 mole of the substance. On a periodic table, which shows all the different elements, molar masses measured in grams are displayed with each symbol. So here's the symbol for carbon on a periodic table, and the number 6 we know is its atomic number. That's the number of protons within the nucleus of a carbon atom. The number underneath the symbol, 12.011, earlier we said it was an atomic mass, average atomic mass of the different isotopes of carbon, measured in atomic mass units. So we'd say an atom of carbon, on average, is 12.01 AMUs. However, we're now going to take that same number and rethink it now as the average, not atomic mass, but molar mass of carbon. So in other words, on average, a mole of carbon weighs 12.01, and now since we're talking about a mole, a huge number, Avogadro's number of particles, we're going to change the units to grams. Now, why can we do that? Why is the same number in AMUs the mass of a single atom as it is here the mass of a mole in grams? The reason for that is that the definition of an atomic mass unit was 1/12 the mass of an atom of carbon-12. Another way to look at it is that there's Avogadro's number of atomic mass units in a gram, and that's what makes this so convenient. This number is the mass in AMUs of a single atom, or it's the mass in grams of a mole of carbon. Now, often most times actually, you're not going to be talking about individual element molar masses. You're going to want to know a molar mass for a compound. So I'm taking here an intentionally complicated formula, iron 3 nitrate nonahydrate, and we want to find the molar mass of this compound. In other words, 1 mole of this salt, what would be its mass? Sometimes it's called a formula mass as well. If I were doing this myself, I would just grab a calculator and a periodic table, and I would just do everything directly on the calculator. But let's jump in and see if we can do it on paper and show some work. So in 1 mole of this salt, we see there's 1 Fe in the formula, so in 1 mole of the salt there would be 1 mole of Fe. There's 3 nitrates, NO3s, so there'd be 3 moles of nitrogen. Each nitrate has 3 oxygens, so 3 nitrates, 3 times 3, there's 9 moles of oxygen. Now if you want, you could also take the 9 moles of oxygen that are out here and say there were 18 moles of oxygen. But what I'm going to do instead is say that this 9 refers to water, and I'll say that there's 9 moles of water. So rather than treat the hydrogen separately, I'll treat the hydrogen and these oxygens as being part of water. So now we're going to go to a periodic table, and we'll convert the moles of iron to grams. So 1 mole of iron, we look up the symbol for iron just like this on a periodic table, and we find its molar mass. 1 mole of iron on a periodic table is 55.85 grams. Similarly, 1 mole of nitrogen is 14.01 grams, and 1 mole of oxygen is 16.00 grams. Now, obviously, you're not going to find water on a periodic table, but let's do some mental math. 1 mole of water would weigh how many grams? Well, in a mole of water, there's a mole of oxygen and 2 moles of hydrogen. So a mole of oxygen is 16 grams, and 2 moles of hydrogen would be 2.02 grams. So therefore, 18.02 grams is the mass of a mole of water. We see that so often that that's a number that'll probably end up just in your head. So 1 mole of iron is 55.85 grams of Fe. 3 moles of nitrogen is going to be, 3 times 14 will be 42.03 grams of nitrogen. And 9 moles of oxygen, I think that's 144, but let me just double check that. Yeah, it's 144.00 grams of oxygen, and 9 moles of water is going to be 162.18 grams of water. So in 1 mole of the salt, we have these masses of elements and of water. So now we can simply add them up, 55.85 plus 42.03 plus 144 plus 162.18, and we get 404.06 grams, and that's the molar mass of our compound. 1 mole of this salt would have a mass of just over 400 grams. Now again, if I were to need this number, this molar mass, in a problem, I would not have done everything we just did there. I would have instead, with a periodic table and the formula beside me, I'd grab a calculator, and on the calculator I'd say there's 1 iron, so 55.85, that's the molar mass of iron. 3 nitrogens, so 3 times 14, let me redo that, 55.85 plus 3 times 14.01, plus 9 oxygens, so 9 times 16, plus 9 waters, so 9 times 18.02 equals, and there's the same answer, 404.06, and it's very, very fast to calculate on a calculator. So there's the molar mass of a compound, the mass of 1 mole. So in 1 mole of iron nitrate, monohydrate, there'd be Avogadro's number, 6.022 times 10 to the 23 formula units of this salt. It's an ionic compound, and it would have a mass of 404.06 grams.